Welcome to DAR Tutors for expert tuition in IB A-Level and IGCSE curricula. Today, we're going to explore a fundamental concept in statistics: linear combinations of random variables. So far, you've likely worked with individual random variables, like the outcome of a single die roll or the height of one student. However, in many real-world situations, we need to consider several random variables acting together. Our goals for this video are to define what a linear combination of random variables is, understand the rules for calculating its mean and variance, and apply these rules to solve IB-style problems involving different distributions. We'll also cover the central limit theorem. Let's begin by formalizing this idea. First, let's establish what a random sample is, a concept we'll use throughout our discussion. A random sample of size n, which we can label x sub 1, x sub 2, up to x sub n, is a set of independent observations taken from the same population. This definition has two key components. First, each observation, x sub I, is a random variable with the same distribution as the original population. Second, these observations are independent random variables. This means the outcome of one observation does not influence the outcome of any other. To put it simply, independence means one outcome doesn't affect the next. This assumption is crucial for the rules we're about to discuss. With this in mind, we can now define the main topic. A linear combination of random variables x sub 1 through x sub n has the general form a sub 1 times x sub 1, plus a sub 2 times x sub 2, and so on, up to a sub n times x sub n. Here, a sub 1, a sub 2, and so on, are all constants. For example, if you have two random variables, x and y, their linear combination could be something like 2x plus 3y. This new linear combination, which is a sum of random variables, is itself a random variable. Our goal is to find its expectation and variance. Now let's look at the rules for finding the expectation, or mean, of a linear combination of random variables. The rule for expectation is very straightforward. It holds true whether the variables are independent or not. The expectation of a linear combination is simply the sum of the expectations of each individual term in the combination. Let's demonstrate with a simple case: two random variables x and y. The expectation of x plus y is the expectation of x plus the expectation of y. What if we have a constant k multiplying a random variable x? The expectation of k times x is k times the expectation of x. So, you can factor the constant out of the expectation operator. We can combine these two rules to find the expectation of any linear combination. The expectation of a sub I times x sub I is the sum from I equals 1 to n of the expectation of a sub I times x sub I, which simplifies to the sum of a sub I times the expectation of x sub I. Let's work through an example. Suppose we have two independent random variables, x and y. We are given their means and variances. Specifically, the expectation of x is 3, and its variance is 3 over 2. The expectation of y is 2, and its variance is 5 over 4. Our task is to find the expectation of the linear combination 2x minus y. First, we write down the expression we want to evaluate, the expectation of 2x minus y. Next, we apply the property that the expectation of a sum or difference is the sum or difference of the expectations. This gives us the expectation of 2x minus the expectation of y. Now we use the property that the expectation of a constant times a variable is the constant times the expectation of the variable. So the expectation of 2x becomes 2 times the expectation of x. Finally, we substitute the given values. The expectation of x is 3, and the expectation of y is 2. So we have 2 times 3 minus 2. Calculating this gives us 6 minus 2, which equals 4. The expectation of the linear combination 2x minus y is 4. Now let's turn our attention to the variance of a linear combination. The rule for variance is different because it requires an additional condition. The random variables must be independent. If the random variables x sub 1 through x sub n are all independent, then the variance of their linear combination is the sum of the variances of each term. Notice that the constants are now squared. Let's explore why the constants are squared. It comes from two basic variance properties. First, for independent variables x and y, the variance of their sum is the sum of their variances. Second, the variance of a constant k times a variable x is k squared times the variance of x. Applying these properties, the variance of a sub I times x sub I is the sum from I equals 1 to n of the variance of a sub I times x sub I, which becomes the sum of a sub I squared times the variance of x sub I. It's crucial to remember that this only works when the variables are independent. Let's continue with our previous example to calculate the variance. Remember our independent random variables x and y. We need to find the variance of the linear combination 2x minus 3y. First, we write the expression we want to evaluate. This is the variance of 2x minus 3y. Because the variables x and y are independent, we can apply our variance rule. The variance of a difference becomes the sum of the variances. This is a common point of confusion. Remember that variance is always added. Also, we square the coefficients. So we have 2 squared times the variance of x plus negative 3 squared times the variance of y. Simplifying, this is 4 times the variance of x plus 9 times the variance of y. The squaring of the negative coefficient is why the term becomes positive. Now we substitute the given variances. Variance of x is 3 over 2 and variance of y is 5 over 4. This gives us 6 plus 45 over 4, which is to 4 over 4 plus 45 over 4, totaling 69 over 4. So the variance of 2x minus 3y is 17.2. Now let's apply these rules to a specific distribution, the binomial distribution. This provides a clear justification for its mean and variance formulas. Consider a random variable y which follows a binomial distribution with parameters n and p. Y represents the number of successes in n independent Bernoulli trials, each with a probability of success p. We can think of this as the sum of n simpler random variables. Let x sub I be a Bernoulli random variable that is 1 if the ith trial is a success and 0 otherwise. Since each x sub I represents a single trial, its expectation is p, and its variance is p times 1 minus p. The total number of successes y is simply the sum of these n independent Bernoulli variables. So y can be written as the sum of x sub I from I equals 1 to n. Let's find the expectation of y. The expectation of y is the expectation of the sum of x sub I. Using our expectation rule, this is the sum of the expectations of x sub I. Since each ex sub I is p, we are summing pn times, which gives us n times p. This proves that the expectation of a binomial distribution BNP is p. Now for the variance of y. The variance of y is the variance of the sum of x sub I. Since the trials are independent, we can use our variance rule. This is the sum of the variances of x sub I. Each var x sub I is p times 1 minus p. Summing this n times gives us n times p times 1 minus p. This confirms the standard variance formula for the binomial distribution. We can extend this idea to another important discrete distribution, the Poisson distribution. A remarkable property of the Poisson distribution is how its mean and variance behave under addition. Suppose we have two independent Poisson random variables, x and y. X follows a Poisson distribution with parameter lambda 1, and y follows a Poisson distribution with parameter lambda 2. X and y are independent. Using our linear combination rules for independent variables, we can find the expectation and variance of their sum, x plus y. The expectation of x plus y is the expectation of x plus the expectation of y. Since the expectation of a Poisson distribution is its parameter, this is lambda 1 plus lambda 2. Similarly, the variance of x plus y is the variance of x plus the variance of y. The variance of a Poisson distribution is also its parameter, so this is lambda 1 plus lambda 2. Notice that for x plus y, its expectation equals its variance. This is a defining characteristic of the Poisson distribution. This hints at a deeper result, and the result is, if x and y are independent Poisson variables, their sum, x plus y, is also a Poisson variable with a parameter equal to the sum of their individual parameters, lambda 1 plus lambda 2. The proof of this result is beyond the scope of this course, but it's a very useful property to know and apply. This means that if you have two independent processes that follow a Poisson distribution, the total count from both processes also follows a Poisson distribution. Let's work through a problem involving the sum of Poisson random variables. A bus stops at two interchanges, A and B. The number of people getting on at AX is Poisson distributed with a rate of 10 people per bus. The number of people getting on at BY is Poisson distributed with a rate of 17 people per bus. We need to find the probability that the total number of people who get on T is at least 30. First, we identify our random variables. X is Poisson with rate 10, and Y is Poisson with rate 17. We will assume X and Y are independent, which is standard for this type of problem. The total number of people, T, is simply the sum of the people from interchange A and interchange B, so T equals X plus Y. Because X and Y are independent Poisson variables, we know their sum T is also a Poisson variable. Its rate parameter, lambda, is the sum of the individual rates. So the total number of people getting on follows a Poisson distribution with a rate of 27. Now we can calculate the probability. We want the probability that T is at least 30. This is the sum of probabilities for T equals 30, 31, 32, and so on. It's much easier to calculate the complement. Using a calculator, we find the cumulative probability for T less than or equal to 29. On most calculators, this is the Poisson CDF function. For a Poisson distribution with lambda 27, the probability of 29 or fewer successes is approximately 0.6972. Finally, we subtract this from 1 to find our answer. The probability that at least 30 people get on the bus is approximately 0.30. There's about a 30.3% chance. Now, let's look at the continuous analog. Linear combinations of normal random variables. Here, the results are even more powerful. We saw that a sum of independent Poissons is a Poisson. The same principle applies to normal variables. The fundamental result is this. Any linear combination of independent normally distributed random variables is also a normally distributed random variable. This means that not only can we find the new mean and variance using our linear combination rules, but we also know the shape of the new distribution. For any constants a sub I and any independent normal variables x sub I with mean mu sub I and variance sigma sub I squared, their linear combination y equals the sum of a sub I x sub I is also normal. The mean of y will be the sum of a sub I times mu sub I, and the variance of y will be the sum of a sub I squared times sigma sub I squared. Knowing the distribution is still normal is a huge advantage for calculating probabilities. Let's work through a classic problem type that tests this concept. The weights of male employees in a bank are normally distributed with a mean of 81.5 kilograms and a standard deviation of 7.3 kilograms. The bank's elevator has a maximum load capacity of 494 kilograms. Part A asks for the probability that the elevator will be overloaded if 6 randomly selected male employees enter it. Let X sub I be the weight of the ith employee. We assume these weights are independent. The total weight, let's call it Y sub 6, is the sum of the 6 individual weights. Since each X sub I is normally distributed and they are independent, their sum Y sub 6 will also be normally distributed. We need to find the mean and variance of Y sub 6. The mean is simply 6 times the mean of a single employee's weight. The variance is 6 times the variance of a single employee's weight. Remember, the variance gets added, not the standard deviation. So the total weight of 6 men is normally distributed with a mean of 489 kilograms and a variance of 319.74 kilograms squared. Its standard deviation is the square root of 319.74, which is about 17.88 kilograms. Finally, we calculate the probability that the total weight exceeds 494 kilograms. Using our calculator's normal CDF function with a lower bound of 494, upper bound of infinity, mean of 489, and standard deviation of 17.88, we get approximately 0.39 nu. This means there's a 39% chance the elevator will be overloaded with 6 men, which is quite high. Part B asks us to recommend the maximum number of males if the overload chance must be at most 0.1%. We found that 6 is too many. If we try 5, the total weight Y sub 5 is normal with mean 407.5 and variance 266.45. The probability of exceeding 494 kilograms for 5 men is an extremely small number, 5.82 times 10 to the negative 8. This is well below the 0.1% threshold. Therefore, the bank should recommend at most 5 male employees use the elevator together. We've seen how powerful our rules are, but what if the original population distribution isn't normal? This is where the central limit theorem comes in. Imagine taking many samples of the same size, n, from a population. For each sample, you calculate its mean. This collection of all possible sample means forms a new distribution called the sampling distribution of the sample mean. We denote the sample mean as x bar sub n. It's a random variable because its value depends on the particular sample chosen. Let's find its expectation and variance using our rules. The expectation of x bar is the expectation of the sum of x sub I, all divided by n. The constant 1 over n comes out of the expectation, and the sum of expectations is n times the population mean mu. This simplifies to mu. So the mean of the sampling distribution is exactly the same as the population mean. We say that the sample mean is an unbiased estimator of the population mean. Now for the variance. The variance of x bar is the variance of the sum of x sub I over n. The constant 1 over n comes out as 1 over n squared. The sum of the variances is n times the population variance, sigma squared. This simplifies to sigma squared over n. This gives us the standard deviation of the sample mean, which we call the standard error. It's the population standard deviation, sigma, divided by the square root of n. This shows that the sampling distribution is more concentrated around the mean than the population distribution is. Now for the remarkable part. What is the shape of this sampling distribution? We've laid the groundwork. Now let's explore the central limit theorem, one of the most important results in statistics. The central limit theorem, or CLT, is a fundamental pillar of statistical inference. It allows us to work with sample means even when the original population isn't normally distributed. Let's summarize our findings so far. We know that for any population with mean mu and standard deviation sigma, the mean of the sample means is mu, and the standard deviation of the sample means is sigma divided by the square root of n. The first part of the theorem states that if the population is normally distributed, then the distribution of sample means, x bar sub n, will also be normally distributed regardless of the sample size n. So, it's n of mu, sigma squared over n. The second and more powerful part of the theorem says that for any population, even one that is not normally distributed at all, if the sample size n is sufficiently large, then the sampling distribution of x bar sub n is approximately normally distributed. It's approximately n of mu sigma squared over n. What is sufficiently large? This is a rule of thumb, but many texts suggest in greater than or equal to 30. However, the exact value depends on how non-normal the original population is. The more skewed the population, the larger n needs to be. In essence, the central limit theorem is why the normal distribution is so pervasive in statistics. It says that for large enough samples, we can almost always assume the sampling distribution of the mean is normal. Let's apply the central limit theorem to a problem. A random variable x has a mean of 60 and a standard deviation of 4. A sample of size 45 is taken. We need to find the probability that the mean of this sample, x bar sub 45, is less than 59. Notice we don't know the distribution of the original population x. It could be skewed, uniform, or something else entirely. But that doesn't matter, because the sample size is 45. Since 45 is greater than or equal to 30, we can invoke the central limit theorem. The CLT tells us that the distribution of the sample mean, x bar sub 45, will be approximately normal. We need to find its mean and standard deviation. The mean of the sample means is the same as the population mean, which is 60. The standard error is the population standard deviation 4 divided by the square root of the sample size, 45. So, x bar sub 45 is approximately normally distributed with a mean of 60 and a standard deviation of about 0.596. Now we can calculate the probability just like any other normal probability. We use our calculator to find the cumulative probability from negative infinity up to 59 for a normal distribution with mean 60 and standard deviation 0.596. The result is approximately 0.0468. This demonstrates the power of the CLT. Even without knowing the original population's shape, we can make confident probability statements about the sample mean. At Dart Tutors, we offer expert tuition in IB, A-Level, and IGCSE curricula. Contact us to learn more and unlock your full potential. Let's work through another problem to solidify our understanding of these concepts. This problem involves comparing two normal random variables. A drinks manufacturer produces two sizes of bottles, small and large. The contents are normally distributed. Small bottles have a mean of 280 ml and a variance of 4 ml squared. Large bottles have a mean of 575 ml and a variance of 16 ml squared. The contents are independent. Part A asks for the probability that a large bottle contains less than twice the amount of a small bottle. This translates to finding the probability that L is less than 2 times S. To calculate this, we must rewrite it as a probability involving a single variable. We can define a new variable, D, as L minus 2S. We need to find the probability that D is less than 0. Since S and L are independent normal variables, their linear combination D will also be normal. We find the mean of D. Using the expectation rules, it's the expectation of L minus 2 times the expectation of S. This is 575 minus 2 times 280, which is 15 ml. Now for the variance. The variance of D. Since they are independent, we add the variances. It's the variance of L plus the variance of negative 2 times S. This becomes 16 plus 4 times 4, which is 32. So our new variable D is normally distributed with a mean of 15 and a variance of 32. Now we calculate the probability. We need PD equals 0. Using our calculator with mean 15, standard deviation root 32, and an upper bound of 0, we get approximately 0.0039. This means there's a very small chance that a large bottle contains less than twice the amount of a small bottle. Part B asks for the probability that a large bottle contains less than the total amount in two small bottles. This is very similar. We define a new variable, say M, as L minus the sum of the two small bottles. So M equals L minus S, sub 1 minus S sub 2. Its expectation is the expectation of L minus 2 times the expectation of S, which is again 15. For the variance of M, we add the variances of L, negative S sub 1, and negative S sub 2. This is 16 plus 1 times 4, plus 1 times 4, which equals 24. So M is normal with mean 15 and variance 24. We want to find the probability that M is less than 0. Using our calculator, we get approximately 0.0078, which is even smaller. Let's quickly review the key ideas we've covered today. These are the foundational tools for understanding estimation and confidence intervals. First, we establish the rules for combining random variables. For expectation, it's always the sum of the expectations. For variance, it's the sum of the variances, but only if the variables are independent, and we must remember to square the coefficients. We saw specific results for the sum of independent Poisson variables, which is another Poisson, and the sum of independent normal variables, which is another normal. Finally, we encountered the incredible power of the central limit theorem. It tells us that regardless of the population distribution, the distribution of sample means, x bar sub n, is approximately normal for large N, with a mean of mu and a standard error of sigma over root n. This means you are now equipped to calculate probabilities for sums and means of random variables, which is a crucial skill for the IB/AI/HL course. To test your understanding and prepare for the IB exam, I've prepared 5 practice questions. I recommend you pause the video after each question, attempt it yourself, and then watch the worked solution. Let's begin. Practice question 1. The number of text messages received per hour. is Poisson distributed with a mean of 12. The number of emails received per hour, E, is Poisson distributed with a mean of 7. Assuming these processes are independent, find the probability that the total number of messages received in a 1-hour period is more than 25. Pause the video here and try to solve it on your own. Remember to think about how you can combine the two Poisson variables. Welcome back. Let's look at the solution to practice question 1. First, we define our variables. T is Poisson with a mean of 12, and E is Poisson with a mean of 7. The problem states they are independent. We want the probability that the total number of messages T plus E is greater than 25. Since T and E are independent Poisson variables, their sum, x, is also a Poisson variable. The parameter for the sum x is the sum of the individual parameters, which is 12 plus 7 equaling 19. So, x is Poisson distributed with a mean of 19. Now we need to find p to 25. It's easiest to use the complement. This is 1 minus the probability that x is less than or equal to 25. We use our calculator's Poisson CDF function. For a Poisson distribution with lambda 19, the probability of 25 or fewer successes is approximately 0.9404. Finally, we subtract this from 1 to get our answer. The probability that more than 25 messages are received is approximately 0.0596. There's about a 6% chance. Practice question 2. A factory manufactures steel rods. The length of a rod is normally distributed with a mean of 200 centimeters and a standard deviation of 0.5 centimeters. The company requires a customer to buy 5 rods, and they are shipped in a box. The customer needs the total length of the 5 rods to be at least 1,002 centimeters for their project. Find the probability that a randomly chosen box of 5 rods meets this requirement. Think about how to define the total length and its distribution. Pause the video and give it a try. Let's review the solution for practice question 2. First, the length of a single rod, x, is normal with mean 200 and standard deviation 0.5. We assume the lengths of the 5 rods are independent, which is reasonable for a manufacturing process. The total length, let's call it y, is the sum of the 5 individual rod lengths. Since y is a sum of independent normal variables, y will also be normally distributed. We calculate its mean and variance. The mean is 5 times the mean of one rod, which is 1,000 centimeters. The variance is 5 times the variance of one rod. Remember to use variance, not standard deviation. This gives us 1.25, so the standard deviation of the total length is the square root of 1.25, approximately 1.118 radius. Now we can calculate the probability the customer needs. We want the probability that y is at least 1,002. Using our calculator, we can find the probability that y is less than or equal to 1,002 and subtract it from 1. Using the normal CDF function, we find that py equals 1,002 is approximately 0.9634. Subtracting this from 1 gives our final answer, 0.0366. So there's about a 3.7% chance a random box of 5 rods meets the customer's requirement. Practice question 3. The weight of a particular brand of potato chip bag is normally distributed with a mean of 155 grams and a standard deviation of 4 grams. The machine that fills the bags breaks down. If the average weight of 50 consecutive bags is less than 154 grams or more than 156 grams, find the probability that the machine does not break down during a production run of 50 bags. This problem involves the sampling distribution of the mean. Pause the video and see if you can solve it. Here is the solution to practice question 3. First, we define our variables. The weight of a bag X is normal with mean 155 and standard deviation 4. We are interested in the sample mean of 50 bags, X bar sub 50. Since the original population X is normally distributed, the sampling distribution of the mean, X bar sub 50, is also normally distributed for any sample size. The mean is the population mean, 155. The standard error is the population standard deviation divided by the square root of 50, which is about 0.5657. The machine does not break down if the sample mean is between 154 and 156 grams inclusive. So we need to find the probability that x bar sub 50 is between 154 and 156. We can calculate this using the normal CDF function. The probability of the sample mean being less than 154 is about 0.0384, and the probability of it being less than 156 is about 0.9616. Subtracting these gives a probability of 0.9232. There's a 92.3% chance the machine will not break down. Practice question 4. The time it takes for a customer to complete their grocery shopping is a random variable with a mean of 15 minutes and a standard deviation of 4 minutes. A sample of 36 customers is observed. Find the probability that the mean time spent shopping by these 36 customers is less than 14 minutes. Notice that the population distribution is not given. Which powerful theorem should you use here? Pause the video and solve it. Let's review the solution for practice question 4. The population mean shopping time is 15 minutes, and the standard deviation is 4 minutes. We are looking at a sample mean of 36 customers. The problem does not state that the shopping times are normally distributed. This means we cannot assume the sample mean is normal just because the population might be. However, the sample size n is 36, which is greater than 30. This means we can apply the central limit theorem. The CLT tells us that the sampling distribution of the mean, x bar sub 36, will be approximately normally distributed. We find its mean and standard deviation. The mean is the population mean, 15. The standard error is the population standard deviation divided by the square root of 36, which is 4 over 6, or 2 over 3. So x bar sub 36 is approximately normal with a mean of 15 and a standard deviation of 2 to 3. Now we find the probability that the sample mean is less than 14 minutes. Using normal CDF with mean 15, standard deviation 2, 3, and an upper bound of 14, we get approximately 0.0668. There is about a 6.7% chance that a sample of 36 customers will have an average shopping time of less than 14 minutes. Finally, practice question 5. The weight of a small chocolate bar is normally distributed with a mean of 30 grams and a variance of 4 grams squared. The weight of a large chocolate bar is normally distributed with a mean of 80 grams and a variance of 9 grams squared. S and L are independent. A large bar and 2 small bars are selected. Find the probability that the large bar weighs more than the total of the 2 small bars. This problem combines concepts of linear combinations and normally distributed variables. Take your time and remember the variance rules. Pause the video now. Let's review the solution for practice question 5. We have the distributions for small and large bars. We need to compare the weight of one large bar, L, to the sum of 2 small bars. Let's call the weights of the 2 small bars S sub 1 and S sub 2. We want to find the probability that L is greater than S sub 1 plus S sub 2. To do this, we create a new random variable, D, which is the difference. L minus S sub 1 minus S sub 2. We need to find the probability that D is greater than 0. Since D is a linear combination of independent normal variables, D will also be normal. We need its mean and variance. The mean of D is the expectation of L minus the expectations of S sub 1 and S sub 2. This is 80 minus 30, which equals 20 grams. For the variance of D, we add the variances of each term. This is the variance of L plus the variance of S, sub 1 plus the variance of S sub 2. This equals 9 plus 4 plus 4, which is 17 grams squared. So D has a standard deviation of the square root of 17, or about 4.123 grams. So our new variable D is normally distributed with a mean of 20 and a variance of 17. We want the probability that D is greater than 0. Using the normal CDF function, The probability of D being less than or equal to 0 is approximately 2.94 times 10 to the negative 6. Subtracting this from 1 gives a probability of approximately 0.999997. It is extremely likely that the large bar weighs more than the total of the two small bars. That brings us to the end of our session on linear combinations of random variables and the central limit theorem. You have now learned how to handle some of the most important scenarios in statistics. The ability to combine random variables and use the central limit theorem is the foundation for much of what you will do in statistical inference, estimation, and hypothesis testing. If you found this video helpful and are looking for more in-depth personalized guidance, please contact DAR Tutors for expert tuition in IB, A-Level, and IGCSE curricula. Thank you for watching.